All right, I think we are in time. So a couple of things before we start. It will be nice if I can see your faces. I had like experiences in Zoom with some classes where it was like really weird just to talk and not see like people's reaction. It's good to have at least like some feedback. So thank you for that. I think we're missing a couple of people, but that is okay. We will start today's session. A couple of things before we start, and I introduce myself and all of that. Yes, I had to modify as I was telling Nico, I had to modify the time for the workshop because of my work. I was as a research assistant, so some meetings were moved to like early morning. So those meetings are like, yeah, they finish around like 10 a.m. They start like really early, so it's like 2 hours, and then I have like 30 minutes to install everything and start the sessions. So I'm planning also on a couple of things, if that's okay with you and it doesn't interfere with your schedule. Because we will do like some really cool things. I will try to be as pedagogical as possible. I've done this workshop other times, so I know that 3 days is enough to cover some really cool things about machine learning and deep learning, especially to give you the tools to continue doing more stuff related to that. But what I want to do, I want to change, if it's okay with you, to change the last session for Monday, because I have one specific reason for that. I will teach you not only how to, let's say, like use machine learning, but also like to train with your own data. And in order to do that, you will need some time. If we do like Wednesday, Thursday, and Friday, probably I won't get to see like your results, or you won't have time to actually do things. So it will be nice to have like the weekend, to leave you the weekend so you can basically test a couple of things that I will teach you. Especially because we will go through like image generation and things like that are quite interesting. If that's okay, fine. If not, let me know at the end of the session. Check your schedules, and if that doesn't work, that's fine. We can do like 3 days in a row. What else? The reason why you were selected for this workshop, I had like a lot of applicants, and that was like shocking. It was nice. More than, I think it was like around like 100. I was not expecting many people because this year I didn't have much time to teach this workshop. Last year I taught a workshop on reinforcement learning and robotics. That was like quite successful. It was like very nice, but intensive, like 1 week, every day, 4 to 5 hours. And yeah, this year I don't have much time for that because of work, and also like I'm finishing my thesis proposal for my PhD. So one of the reasons I was saying that why you're here is that even though I get like a lot of applicants for the workshop, I was interested in doing something that was like more introductory, and I don't want to say like basic, but that is more suited for people that are just entering the world of machine learning, to understand like basic concepts and to understand, basically to understand a little bit what is going on under the hood, for example. Because I don't know, some people, they were already like doing like, I don't know, like a PhD in computer science. And probably that person already knows everything that you need to, what I will teach. I mean, I know what I need to teach you, but probably like, yeah, that person knows way more. So I don't see the reason why. Or for example, like people that expert in C++. If you're expert in C++ and also like a lot of math experience, you don't need this. So you can play on your own, and that's fine. I mean, I would love to exchange experiences with those applicants, but I was like more inclined to, also because of your work. I mean, I took like a full day of reviewing applications, and I saw that there is something about like the reasons and the work that you show. So that is something that kind of explain why you were selected, because sometimes you do want to know. I saw that many of you are. I thought that many of you are. I saw that many of you are in an undergrad, for example, or just starting like a grad program, or again, like just starting with like coding or things like that. And that is always good, because that's where I think the best questions come from, the most helpful for a group, right? When you are a PhD in computer science, probably you will ask me about like some weird hyperparameters of a model, and of course we can talk about that, but other people will be like, I don't know, like won't understand much, because that is, I'm doing my PhD here at MIT, and that happens every time that I go to like a hard class, and there is someone that knows too much and asks something, and usually I am the one not understanding anything. I'm surrounded by 100 people, and everybody's like, "Whoa, yes, good question," and I'm like, I don't know what they are talking about, because I am not a computer scientist. I am an architect. So I will do a brief presentation, then we'll have some time so we get to know each other. And then we will go directly into coding. I will teach you, today we will do something that is like basic, but is necessary to understand how this will escalate tomorrow in the last session. Because if we understand this, we will understand why we will be doing the following things, or the next things in the following sessions. So can you see my screen, right? I'm sharing my presentation. Okay. Okay, my name is Diego Pinochet. I am from Chile, from Santiago, long country at the end of the world in South America. I am close to turn 40 in a couple of months. I will start my 4th year in the PhD Design and Computation program at MIT. I was before at MIT in between 2013 and 2015 doing my second master's degree, SMARCS, at the same group, Design and Computation. And I started in 2018 my PhD also in the same group, Design and Computation, doing research around mostly like the relationship between design, computation, and technology, because the group has a very particular vision about what computation is. All types of computation, not only digital computation, that what we see usually, or what people understand what computation is. It's more about like calculating in a way of thinking. But I'm particularly interested in that relationship between technology and design. I was presenting some of that in the last Saturday in the PhD consortium at Digital Futu5res. It was not a very good presentation. I was like tired, and also it was really hard to compress 45 minutes presentation into 15, so I didn't have much time. But I mean, more or less, you understand that if you see that it's available on YouTube, you will understand on what are the type of things that I do that are more oriented into like more interactive technologies for design and thinking and so on and so forth. As I was saying, I'm close to present my thesis proposal. That is something that you usually do at the end of the 3rd year, where I am right now. So before starting my 4th year, I will be ready with my proposal, and I will have 2 years to finish my thesis, because this is a long 5-year PhD program. So it's a let's say it's quite a journey that you have here. So today I will start again with this presentation. The workshop is machine learning for design and creative purposes. And yeah, the goal is that you can basically start using what we are doing today and maybe applying it to other type of, I don't know, your projects, or combining it with different workflows. Because we will try to understand what is going on, not only learn how to press play and generate something. We will go through, for example, things that are usually like necessary, like object detection, image generation, and some interactivity. And we will try to also interact or create like a bridge, for example, to communicate what we do, mostly in using Python, because machine learning, usually you work and you find more resources in Python. It's easier to do machine learning in Python, and communicate that or translate that information, let's say, to like Grasshopper or Unity or processing or any software that you're interested in using. Again, this is, I don't want to call it like a basic level workshop, because we will do actually quite complicated things, but it's not for someone that already invested some time learning machine learning, right? Or doing machine learning, because probably they are like, yeah, that type of person already knows what to do. So I will start the presentation today explaining a little bit about, giving you a little bit of context. First, like, what is artificial intelligence? We usually see a lot of, I don't want to say like misuse of the word artificial intelligence, but usually you see a lot of people talking about artificial intelligence when they really want to refer to machine learning, for example, or deep learning. And those are two different things. So in short, basically, like, AI is like any computer program or any computational program, not necessarily digital, but usually are digital computers that do AI, that does something smart, right? And when we go to like a definition about smart, is having or showing a quick-witted intelligence, program so as to be capable of some independent action. And actually, that the second definition, it's a little bit more precise for what machine learning is, for example, right? Or what the smart definition applies to machine learning. In this case, it's like to show some independent action. So basically, you want the computer to compute something for us, and to basically you as the spectator of that infer or basically have some insights from that independent action that the computer will take in the form of an object detection, object tracking, image generation, predictions, regressions, and so on and so forth. So we see today, right, that machine learning is something super, super popular. Like everybody, and I was saying this, and some people got a little bit mad in the presentation on Saturday, that everybody wants to jump into the bandwagon of machine learning. And that's true. I mean, it's interesting. Everybody wants to do it. And we are living like interesting times in terms of that, because even though not many people understand what machine learning is doing, sometimes I don't understand most of the things. It has been like quite a struggle to understand what's going on, basically, but it's always there. And we see usually like this type of things, right? We see like networks and brains and some like images of like some basically like combining like half a brain and half like gears or like some sort of engine. But what is interesting about this is to understand also, again, like the difference between like AI and machine learning. And machine learning is a subset of AI. Not all AI is machine learning, right? But all machine learning is AI. So that's a difference, because AI is like way more, let's say, like broad than that. There are like different types of AI, for example, starting from people that during the 60s were doing like graph theory, and search, for example, or things that are not necessarily related with the type of machine learning that we will use, or the type of machine learning that you listen to people talk about today, right? And we also see this term basically like deep learning, and deep learning is basically a subfield of machine learning. So we have AI, machine learning, and deep learning. And basically this is concerned with algorithms inspired by the structure and function of the brain called artificial neural networks. Basically, like also like AI is based on artificial neural networks, but we can say that the difference between like machine learning and deep learning is that deep learning adds more layers. That is something that I will explain next. In order to replicate some, let's say, structures or functions of the brain. And in the world of machine learning, especially, we won't go to deep learning yet. We have different types. The most popular are supervised, unsupervised, and reinforcement. Right? Supervised is basically like a task-driven type of machine learning, where you have regression and classification. Let's say you have a data set, you have a lot of data, and you have data labeled, and you want to predict, for example, what is in an image, or basically predict, predict based on basically like data that is available, right? Predict a number or predict like some sort of like gradient. So it's called supervised because usually you perform it with labeled data. So for example, something that not a lot of people know, each time that you want to sign in, for example, for an email account or like a different platform, you have the famous CAPTCHA, and you have to prove that you're not a robot. And you click that I'm not a robot, and you will see usually like a grid, like a 3x3 grid with images, and you need to basically like select the images that shows like a bus or a crosswalk or a car or motorcycles or bicycles. Basically what you're doing, you're working for Google or other companies, and you're labeling their data. So basically they compare that if you click on a bike, you will see like, oh, this image is from a bike. So basically they save that information and they use it to train, for example, algorithms or data sets for self-driving cars. So basically that's the idea. You have a data set that is labeled. This is a flower, this is a cat, this is like whatever. And we can train that. We can use that to actually train a neural network to teach the network how to identify or classify things. When we have unsupervised machine learning, it is related to when we have a lot of data. Let's say people clicking all day, like billions of times around like content on the internet. So basically you have a lot of data and it's hard for you to make sense out of that data. So you have a type of machine learning that allows you to understand and generate, basically make patterns around that data. So usually, I don't know, like in urban design, for example, when you apply it to urban design, usually you want to cluster information, for example, or in science, right? To identify like clouds that tells you, oh, here, for example, like this point around like these values are more, I don't know, if you're a doctor looking for cancer, like, yeah, this shows like, yeah, this population here in this cloud of points are more like, I don't know, like prone to get like some sort of cancer than the ones that are here. And usually you see like point clouds like grouped by color or things like that. That is the type of unsupervised machine learning that is more data driven. You want to find like some sort of like order in your data. And reinforcement learning, that is something that we won't see today, but I will point you to the videos on my YouTube channel from to the links of the workshop that I taught last year. Those are all online. I hope that I will have time to actually put this also on my channel to share it with you and everybody. So I will those are like almost like 20 hours of reinforcement learning, and it's like pretty similar to this. I have a presentation, and you can basically go through it. But basically, like reinforcement learning is how a machine basically can learn reacting to an environment. So the typical analogy, for example, is like the baby that is learning how to walk. The baby knows unconsciously that it can move like the arms, and it can move like the legs, and it can move the head to generate like some sort of like balance or equilibrium, right? And by moving the limbs, right, given a stimulus, for example, like the mommy or the dad is saying like, come, and the baby starts like moving like randomly. And then at some point, everything, it starts like improving over time, right? The baby basically like first is like the dad or the mom just like holding the arms of the baby, so it can learn how to put one leg in front of the other. And the babies start like walking like if they were drunk, right, and very clumsy, until they basically know how to walk, and then they become a nightmare because they're running everywhere and jumping on furniture and so on and so forth, right? So basically what a baby is doing is going through a process that is similar to what reinforcement learning is. You have an environment, let's say your built environment, you have a stimulus, the mommy calling the baby, and then you have a set of actions, right? And some sort of like policy that tells you that, oh, put your left leg in front of the right leg, then the other one, and also move your arms to keep balance in your head. So over time, basically like each action improves, because basically you have like some sort of like critique mechanism that is like evaluating if your actions are good, right? And if you go to the goal, and if you go to your mommy, you will get like the reward that is a kiss, that is like, I don't know, like breastfeeding or whatever. And then you know that if you do those actions, you will learn how to do it again, so you can get your reward. It's the similar thing with a dog, right? With a treat, basically, you give a treat to the dog, and the dog knows that applying a certain like policy and sequence of movements, it will be seated and it will get a reward, right? If the dog doesn't do it, it will be punished. Not like hit that, but basically the punishment will be like not getting the reward. And in machine learning, it's the same thing. So if you want to learn more in detail, because for me, it's like the most fascinating type of machine learning or deep learning technique that it's out there, is specifically reinforcement learning. And you can see amazing videos from OpenAI, for example, just like humanoids learning how to walk, and they walk like if they were like zombies, but in the end, after like, I don't know, 1 million tries, they learn how to walk. And it's amazing, because you don't explicitly teach something how to do something, right? So whatever the type or whatever type of machine learning or deep learning that we want to use, or artificial intelligence in general, they are all based on one thing, that are these neural networks that are some sort of like universal function approximators. So it is believed that with neural networks, you can solve almost like any problem in the world. And there is a debate. I mean, in theory, yes, or with a Turing machine, yes, you can solve like almost any problem. Of course, if you can discretize and systematize, or I don't know, like basically reduce anything to numbers. So it is believed, or that is the assumption, that with this neural network, it is like some sort of like universal function approximator. And usually what you see in this image, and I will explain it in a bit, you have inputs and you have weights, right? I will explain what those are. And then you have a function. That is a function that activates or triggers a neuron to contribute to the overall calculation. So usually what you want to do is like minimize like error, for example, in some techniques, right? Through a loss function that is called. I will explain that also in a second. And usually the structure of neural networks that you will see are usually like this. They look pretty similar to a grasshopper definition. If you have used grasshopper, you can see that always you have like an input, then you have like some sort of black box, right? That in this case are called hidden layers. It's a set of layers that are hidden and connected in a specific ways, and also activated according to like certain parameters that are the weights that I just talked about, in order to get an output, right? But the idea is that these neural networks are kind of like cyclical, or like kind of like closed loops. So basically it's a loop that you will run a certain amount of times, like steps, but also like epochs, in order to try to minimize the error or the loss of the function to get better and better. I will explain that also next. But a little bit of history. I mean, it's okay that we also acknowledge a couple of things. Nearly a century before neural networks were first conceived, Ada Lovelace described an ambition to build a calculus of the nervous system, right? And although speculative analogies between brains and machines are as old as the philosophy of computation itself, it wasn't until Ada's teacher, the famous Charles Babbage, the Babbage analytical engine, that is that he proposed the analytical engine, that we conceive basically these machines as calculators, having human-like cognitive capacities, right? And even though like Ada would not lead to see her dream of building the engine basically like manifested like physically, as engineers, basically because of there was no enough like, let's say like hardware development to actually see it working. But that basically those are the foundations of the computation that we have today. Also, we have, of course, like Alan Turing. The ideas, for example, of this analytical engine, or this idea of having like a human-like type of machine calculating something, of course, passed and over time. And for example, like Alan Turing, who cited Ada's Lovelace's work in the as the inspiration for the imitation game. Then he called it, of course, the Turing test. Basically, his like ruminations, for example, into the extreme limits of computation incited the first boom of artificial intelligence, right? Setting the stage for the first, like, let's say, like, golden era of neural networks. And there has been like a recent reemergence of neural network, and of course also like revisiting the history of Alan Turing. Sorry. What else? So basically, he was proposing, or neural networks were first formalized in the late 1940s in the form of Turing B-type machines. There are many types of Turing machines, most expressed in Alan Turing's thesis. There are some also like mysterious like O machines that are oracle machines that can basically, in theory, he never explained that, can solve like any problem, basically, and work like as some sort of like oracle. And basically, these machines drew upon like earlier research into neuroplasticity, for example, by neuroscientists and cognitive psychologists, studying the learning process in human beings. So, for example, we can say that as the mechanics of the brain development were being discovered, computer scientists experimented with idealized versions of action potential and neural backpropagation to simulate that process in machines, right? There was a huge, sorry, this is Alan Turing. There was a huge, like, let's say, amount of research and effort to replicate human brain inside a machine. Especially when we see like pictures like this, right? Today, what we know that this analogy, we know that this analogy here that I'm showing in this image can be taken so seriously, right? This idea of what you see here is the image or like a diagram of actual like human neuron, where you see like the nucleus, you see the axon and the terminals, and some other parts, and that inspired like this type of abstractions, right? Like this, like basically like showing some sort of like flow of information. And then what we see here, right, is like the computer version of that diagram. When you see basically a set of inputs from x1 to x3, something that b in this case is like some sort of function, and y being the output. And that was like the computer model that researchers adopted in order to develop current machine learning, right? So we saw like that with years, like neural networks took a big step forward. With Frank Rosenblatt, for example, devised something that is called the perceptron in the late 1950s. And again, like during the 50s, like post World War II, there was like a huge amount of money that was going into this type of research, especially here at MIT, where the computer-aided manufacturing era started, mostly funded by the military, because there was a need of production, automated production. But at the same time, investing in like automation and machines, there was the need for having like some sort of like interactive system or intelligent system that can control the machine or produce the information for that. So that was the time where computers started to get like bigger and more powerful, and labs around that idea of developing like artificial intelligence started to become like the main, let's say, like force driving or initiating labs around the world, and also like here at MIT. So the perceptron, it was a type of like linear classifier. It was funded by the US Navy, and basically the Mark I perceptron was designed to perform image recognition from an array of photocells, potentiometers, and electrical motors. So basically, the effectiveness of this first perceptron basically made people think, or like, for example, like the New York Times in 1958 to talk about like how soon computers will be able to walk, talk, see, write, or reproduce itself and be conscious of its existence, right? We see some theory, for example, in like von Neumann about like self-replicating machines. But that was the main idea. And we're talking about the 60s, right? 70 years ago. And we saw also like a lot of theory around this idea of like perceptrons, or specifically like machines that can sense something and then give you like some sort of output. We see this famous book from Seymour Papert, the inventor of Mindstorms, and Marvin Minsky, one of the fathers of AI. He died a couple of years ago. He was a professor at MIT, and he made a lot of predictions about what AI will be in the future, right? So basically, in this 1969 book, Perceptrons, it demonstrated various, like even trivial, like limitations of AI by the time, leading to a decline of interest between the academia and the general public. And that is something that is really important to acknowledge. And I know I'm extending a little bit on the theory, but it's necessary. After the boom of artificial intelligence in the late 50s and during the 60s, and development of like personal computation and more powerful machines, there was like some sort of like disappointment, because many of the promises of AI were focused on like having, let's say, like something pretty close to a human. And because of hardware limitations, mostly, and the lack of more like research, yeah, the things that computers were able to do were not like super fancy, let's say, right? So there was a lot of also like criticism from people like Searle or Howard Dreyfus around like computers will never be as good as humans, right? That was the main claim. But something happened, right? I'm not saying that computers now are as good as humans, because my thinking is like completely opposite to that. I think humans are irreplaceable and unique, and computers are pretty good, but something else, right? I don't think computers compete against humans. But there was a major breakthrough starting probably like 2009 to 2012, where neural networks became, again, like dominant and super popular. So the resurgence was largely brought about, or basically by the emergence of convolutional neural networks, which have surpassed sometimes dramatically previous state-of-the-art methods for key problems, for example, in audio or visual domain, right? What during the 80s, for example, were called like expert systems, were replaced with this idea of like machine learning. Now the term was coined and was boosted by the invention of specifically convolutional neural networks. But more interestingly, they have for example, a number of applications and properties not seen before, especially of a kind that has been of interest of artists and other peoples from outside the AI field properly, right? So for example, now today we see convolutional neural networks, and this is what we're going to do and learn how they work today to move to something a little bit more complex. But this is like the more basic thing that it's good that we understand in order to move forward. So we're like the baby, we will learn how to move in order to crawl, in order to walk, hopefully in 3 days of workshop. So this is basically Jan LeCun is the inventor of the LeNet-5 and a convolutional neural network for digits recognition. And you see that there's like the previous diagram of machine learning that I showed you here, right? The computer version. Now, or the perceptron start to look more like this. These are the type of diagrams that you see in most of the papers if you want to get or dive into machine learning, right? So let's consider, for example, like a linear classifier, right? Let's talk about this idea of classifying things, of giving an input to a computer so the computer can give us like some sort of like answer. Let's say you present some object or some data to the computer, for example, like this thumb drive. You don't know what it is, or you want the computer to recognize what it is. The computer would take this information and, according to some like functions and mathematical operations, will more or less give you like an answer. This is a thumb drive. This is a piece of chocolate. This is a miniature cell phone, whatever. And let's consider, for example, like a simple 2D linear regressor classifier in the form of that function over here. And it can be expressed in like any number of dimensions. So in the case of a classification, we can use this to predict a class given certain inputs, right? 1 if x is bigger than 0, or 0 if f of x is less or equal to 0, right? That is a simple thing. Like, give me 2 answers based on some sort of like a classifier. And that was the main idea. And this is tightly related to the idea of an activation function, right? This is the unfamous now Siraj Raval. This was a guy that probably like 3 years ago was like at the peak of popularity on internet. If you wanted to know machine learning from scratch, you will go to this guy's videos, because he was like a super personality, like with the you know, like the double color hair and like super like, I don't know, like extravagant type of guy, like explaining things. He has a very good video though about which activation function should I use. And basically he explains what an activation function is. These were like really short videos. And you get like a very good idea of what an activation function, or basically that this, what basically it's inside a neuron to perform like some certain calculations. So you will see that some functions are like, usually you will listen or you will see like sigmoid function, for example, like or ReLU function, linear or leaky ReLU, sorry. So we can express that, for example, as this. This is like the sigmoid function that we have here, right? And I'm showing you this because we will use these things to calculate what is it's going on, right? So for example, also we can what we see here, for example, is the typical structure of an artificial neural network, or ANN, right? Where again, you have inputs, as many as you want. You have something that are called weights, that is like some sort of parameter or like factor that will be multiplied by the input, and that will be passed to the neuron itself, and that will be calculated through basically calculating a sum and modified by some sort of like bias. And then an activation function basically will determine if this triggers, right, this neuron actually activates, or basically makes the calculation and contributes to the overall calculation of your neural network. So imagine this multiplied by many layers. So basically this will give an output, and then you will get some sort of like prediction or classification. So let's, now that we have described, for example, what a neuron, artificial neural is, sorry, we can now define a neural network, right? And a neural network is composed of a series of layers of neurons, such that all the neurons in each layer connect to the neurons in the next layer. So for example, note that when we count like the number of layers in a neural network, we only count the layers with connections flowing into them. We omit the first input layer and the output layer. So for example, the above figure is a 2-layer neural network with 1 hidden layer. And it contains 3 input neurons, 2 neurons in the hidden layer, and 1 output neuron. So we will see that the computation, for example, starts with the input layer on the left, from which we pass the values to the hidden layer. And then in turn, the hidden layer will send its output values to the last layers, which contain our final value, right? And we might know that it might look like the 3 input neuron sends out multiple values because each of them are connected to both of the neurons in the hidden layer. But really, there is still only 1 output value per neuron, and it just gets copied along each of its output connections. So neurons always output 1 value, no matter how many subsequent neurons it sends it to. All right, so we will understand this in a second. So let's consider this, and these are examples taken from Gene Kogan website, right? These are not my examples, but these are very graphical and good to understand what is going on. So let's suppose we have a data set with 1 point, right? That is X, 2.9, 0.3, 1.3, and we have an output value that is 0.65, right? So we will do something that is called forward propagation, that basically is to do a forward pass of these values. And we will try to see through this calculation how everything is working, right? So now we will try to feed a 3.2.1 neural network with a sigmoid activation. So we will also consider for the first layer a set of random weights and biases, right? And we will understand what these are. So we have we have an input, we have an output that we want to basically like predict or classify. We want to get closer to that value by doing a forward pass of X through this neural network. But also this will be determined by this idea of having weights. And this is a key term in machine learning or artificial neural networks, because basically these are the things that get calculated over time that will allow you to have an efficient network or not. We will see that. So usually when you have something like transfer learning, for example, or when they say like download this model, basically what you are downloading beside the architecture, you're also downloading the weights that were already trained or fine-tuned to make a prediction. Let's say this is a model that predicts dogs versus cats, or babies versus, I don't know, like birds. And the biases are some parameters that will modify also the calculation of the activation function. So those weights are going to be here in each connection, and the biases will be in the neurons itself of the hidden layer. So for the output layer, we can consider another set of weights and a bias for the final neuron of, in this case, like -0.2, right? So basically the neural network or the neural networks get populated by this idea of weights and biases. So if we feed our data point, let's say the 2.9, 0.3, and 1.3 to our neural network, we can start calculating our forward pass, right? So if we go, the first calculation according to the function that we have, we'll be doing this mathematical operation where basically you multiply the value by the weight, and then you sum all of those values that go inside the neural network, and then according to the sigmoid function, you will get a value, right? And if we do that with the following, the other neuron, basically you will get another value, and those get passed to the final neuron, the output layer, and you can see that the calculation, right, applying something that is called the mean square error, that is what we have here, we see that this calculation is not quite right, right? We see we wanted to get a value of 0.65. That was our prediction, the value of y. But by using that calculation, we can see, or we can calculate how that the value first is wrong. It's not 0.65, it's 0.29. And we can measure how wrong we were, right? How far are we from the result using the mean square error. That is like basically subtracting the value that you want to get versus the value that you got, and then you square this value and you get a result of 0.130. And that is exactly the value that you want to that you want to minimize, right? That basically that is the most basic idea of like machine learning, basically, or this type of machine learning, is that you have some values, you have some weights, you have some bias, you do your calculations, you do this forward pass, and then you measure how wrong you were. So you will, basically we can relate this to the main concept that you will listen a lot, is about the loss function, or basically like the error. And what you want to do in machine learning is to minimize that error in order to get a good result. If you have any questions, you can interrupt me, or if you want, you can write it in the chat. I have the chat here and you can ask me, but we're going through like really basic stuff that we will implement in code in a second. But now let's imagine that magically we have, right? Magically, we will have a set of ideal weights, right? Let's assume that something magic happened and just did like boom, and then instead of having the initial weights, we have the ideal weight for this neural network, and also like the correct like biases. For the first, like the input layer, the hidden layer, and the output layer, right? So this magic is what happens in the learning phase, actually. So how neural networks are capable of learning, and basically what they learn, what a neural network is learning based on that calculation of the error, they learn how to update the weights. Basically, they learn how to fine-tune themselves in order to make the right predictions, right? So what you see here, for example, is the right calculation based on those weights. So you see that the hidden unit, you see the calculations for each of the hidden units. You get like the values here in the hidden layer, right? And then you have an output that is 0.65. And this happens because we can, that magic that happened is basically like repeating the process over and over again, trying different values and self-tuning until you find basically that the error, the MSE basically is like decreasing over time. And this is quite useful because this is exactly what happens when you have, for example, classification tasks, right? And in the case of like image classification, that is kind of like one of the most basic machine learning techniques that you can find, right? Image classification, where you have your data set. You have, in this case, like the famous MNIST, that is the handwritten data set. You will find this all the time, this famous like numbers, until you get sick. So basically, we will move now with this idea of forward pass. We will move to a more or real world example. Sorry. We will learn how to recognize and label images, right? So if we see this data set, contains 60,000 label images of handwritten digits, basically, that have a size of 28 by 28 pixels, whose classification accuracy serves as a common benchmark in machine learning research. Sometimes when you read a paper, you will see that, oh, our model performed like this fast using the MNIST dataset. You will find that phrase like a lot. Or our model show like 200% faster results than the previous implementation using the CFAR. That is another data set that is out there. Because this benchmark, you will see them a lot because they serve as a benchmark for some models, right? So here we have a random sample of images found in the data set. And the way we set up a neural network to classify these images is by having the raw pixel values be our first layer. Basically, we take all the pixels and we make the first layer of our neural network with those raw pixel values. And we have, in this case, not one output, but we have 10 output classes. One for each of our digit classes from 0 to 9, right? So we have 10 output classes. And since they are grayscale image, each pixel has a brightness value between 0 and 255, being like 0 is black and 255 is white. And all the MNIST images are 28 by 28 pixels, so they contain a total of 784 pixels. That is super important. So we can enroll this into a single array of inputs, like the figure here. So for example, if we take like the 8, let's say we take an 8 from here, these are 28 by 28, and then if we express this in a matrix of pixel values, the amount of white or the amount of black, basically, you will see that represented like this, right? But also in a neural network style, you will represent this as this, like your first network basically will have 784 input values. And again, this concept, and sorry that I've been talking a lot, but I want you to understand that this concept will be there all the time when you're working with images, because you need to always like take into account how to express or how to input the values in your neural network. That is a huge part. I mean, I know like collecting data and formatting your data is super important, but if you want to move forward and do your own stuff, you need to know how to express your data in order to input this to your neural network so you can output something, right? So what else, for example? It's important to realize that this network, even though like this network seems like a lot more imposing than our 3.2 by 1 network before, it works exactly as before. basically the principle of weights, biases, and inputs and outputs is exactly the same, right? It just has like way more neurons. So each neuron in the first hidden layer receives all the inputs from the first layer. And for the output layer, we'll now have 10 outputs rather than just one, with full connections between it and the hidden layer as before. And one of the, each one of the 10 output is assigned to one class label. So basically, in this case, you want to predict something as a 0, as a 1, as a 2, or as a 9. You will get a class for it. So the first one is for the digit 0, the second for 1, and so on and so forth, right? That is like the basic idea of classification. And more or less, this is how things look. So after the neural network has been trained, something that we will talk next, we can predict the digit associated with unknown samples by running them through the same network. So this is also important. When you have a data set and you want to work with machine learning, you have, let's say, 100 images. And usually what you want to do to train your neural network is to get a chunk of those images that is called the training set. And you will reserve another chunk that is basically the validation data set. Why? Because you will train, let's say you have 100 images, and you will train your neural network with 60 images, like 60%, or 80 images, like 80% of your images. So the network will learn how to fine tune like the weights and the biases and so on and so forth. And then you want to train how effective your training was or your neural network is working by feeding unseen data, right? You don't want the network to see the same things that it got from the training process. You want to input something new. So the predicted digits basically will, what you will get as an answer, for example, in a model like this, because you have 10 output labels, you will get like some sort of score for each of predictions. So let's say this is a 9, right? You input this 9, you will have like a lot of like fully connected layers, meaning that you have cross connections. Like this input is connected to all the other neurons, like basically everything is connected to everything. And you will do this calculation and you will get like, let's say like a 0.0 value for 0, a 0.05 for 1, a 0 for 2, and so on and so forth. But you will get, let's say like a 0.98 for 9. So basically you will pick always the highest value as your prediction. And let's not go to this website. I will show you.
I had a quick question though about to your presentation. Just so I'm still grasping it, and I'm kind of might be a little redundant, but so for the weights, you're manually adjusting the weights to each one of those nodes and biases until it gets roughly correct. You had mentioned though that it will adjust itself. I'm still a little confused on how it could adjust itself, and you also manually adjust.
So basically, you will see this in a second. So basically, it's like when you get the first, like what I showed you was a forward pass, just like a simple one pass calculation over this simple 3x2x1 network, right? And then you will calculate the mean square error. So then basically what you will do, you will adjust, and that is something that we will see in code, you will adjust the weights based on that output value. So you will change the initial weights and you will try again. In some models, for example, those are completely random numbers at the beginning. I mean, usually those are random numbers, but then they get like adjusted. So basically, you basically what the network is doing is like measuring which neurons, for example, contribute more to like the proper calculation. So this is why you will have some neurons like activating more than others. I mean, there are a couple of concepts that I will explain, that are related to this idea of specifically for convolutional neural networks that I will explain next. But let me see. I want to show you. I lost the link, but because my link from this presentation was not working. Model builder C sail MIT deep learning.js. Probably I will people. I cannot find it. Let me see if I can find it in images. Model builder. I want you to see specifically this website because I want to show you a way to build your own networks without code, so you can understand what I just explained. Maybe with deep learning JS, I will see something. Sale. I don't think they put the website down. Hopefully not. There is deep learn. Maybe like that. I will find it and this is not finding it. Model builder. No. Maybe I can see it here. Browser demos. No, this is not. I will find it, and I will find it later. I know I have it somewhere, so that's fine. So I will show you one more thing. And it's about this idea of convolutional neural networks. That is something that we will use a lot for this class. Just let me open that presentation. I will go like a little bit faster for that presentation so we can start coding actually.
What will we be coding in? What language or IDE or I don't know.
Oh, I will let you know. I mean, we will use Google Colab because of two reasons that I will explain. But basically, it's because you have cheap computational power to do not only predictions but training also, and that has many reasons. One of the reasons is like of course, the shortage on GPU. On GPUs, like today, you cannot buy. I mean, you can buy, but for like 10 times the price or 5 times the price of a GPU. So that is like I'm trying to find presentation that I know why I closed it. It's like, so again, as I put in the description, of the workshop, like it is important to not only use but understand what is going on with neural networks. I cannot find the presentation. Just 1 second. Oh, it's this one. Nope. Just 1 second. I don't know where did I leave my presentation. I just closed it, but now I don't see it. and again, why Python, for example? And today you can use, basically you can do machine learning with a lot of languages. Python is the one that is like most popular because most of the frameworks, we will see like TensorFlow or PyTorch that are the most popular ones, are based on Python because it's like the most used language for computer scientists. But you can do like C++, or you can do like Lua or Julia, or even like, I mean, it doesn't matter the language, but the frameworks, basically, because if you're not a computer scientist that want to start from scratch, it's good to go through those packages. Just one more second. Spring classes. Oh, I have it here. Okay, I had it locally. Can you see the PDF?
Yes.
Okay, so this was for another class that I used that I taught at the Bartlett School of Architecture. Let me put this full screen. And we will go through this, and in the second part, then we will take a small break, and we will start coding something, right? Full screen. Okay, there we go. So basically, the idea that we just talked about neural networks and inputting like an image with raw pixel values is key to understand, for example, how convolutional neural networks work. So usually when you want to do like image detection, what you want to extract or what you want to get from a specific detection or a specific calculation or model is how can you, for example, get a specific image features, right? Recognize some features, like some sort of like order or entropy or recognizable, yeah, like characteristics of an image to predict like, oh, this is a zero, sorry, this is a face, this is a person, this is a nose, this is a car, and so on and so forth, right? So this is super used, for example, for again, like especially like computer vision detection techniques are super used, for example, for today's like robotics, when you want to do like robotic manipulation. That is basically how to teach a robot how to grasp something and move it from one place to the other. But basically what we want to understand is like what is going on under the hood, because we will use, again, this principle for way more advanced things. Like we will see, for example, like the famous GANs, right? The generative adversarial networks that are super popular nowadays. And we see a lot of people talking about GANs and things like that. Imagine, right, a toy convolutional neural network. And basically we will imagine, right, a two-dimensional array of pixels, basically a grid of pixels, just as the one that I showed you before, the 28 by 28 pixels. Sorry about the noise. Some are doing some construction work in the background, so hopefully that will finish soon. And basically what we will do, we will feed this array of pixels into this convolutional neural network to predict if this is like an X or an O, right? Instead of predicting handwritten digit numbers, we will understand, like with this example, if something is an X or an O, like this, right? If we feed a grid of pixels as an X or an O, we will make this our network to predict this. What is the problem with this? Or what is the problem with most of, or like the earlier, like perceptron type of neural networks that can recognize something, right? You have trickier cases, just like the handwritten cases. You can have something that looks like an X, but it doesn't have the same, let's say, like distribution of pixels like than this ideal X or this ideal O. So you will find, cases like this, a little bit shifted toward like the left upper corner or like smaller, right? You will have like cases related to like kind of like a fine transformation, right? Like translation, scaling, something like rotated, or something that has more weight, basically like a thicker X or a thicker O, right? So those are cases that are triggered for a simple neural network to perform some sort of like classification or detection, right? So this is where convolutional neural networks became like super good, right? This principle. And because deciding for a machine is hard, right? It's super hard. The machine can basically, we as humans can understand that this is an X and also this is an X, right? For us, it's like super simple, but for a machine, because the way they see this is different, or basically we see in a different way as machines see, that for a machine is like super difficult to understand if the image on the right is also an X. So this is what a computer sees, basically, right? We will imagine that values like black pixels are -1 and white pixels are 1. And this distribution, because basically like computers learn this way, that this distribution of pixels or values is different to this distribution of values, is that a simple computer or a simple neural network cannot basically tell you with confidence, with great confidence, that this is an X as well. So basically, yeah, the computer will get like some dissimilarity between the ideal, what you want to predict, and what is actually being predicted, because these are like the differences, right? So because computers are literal. And what convolutional convolution neural networks, or ConvNets, right, or CNs, for the purpose of this workshop, they start from a principle that basically they want, instead of like matching the full distribution of an image, you want to match pieces of those images, right, to detect those features, right? Just like this. So basically you want to match this to this that looks kind of similar, right? Or imagine that if you're trying to detect or classify a human face, basically the distribution of the eye, even though it's like because of genotypes and phenotypes, right, are different. My eyes are different to all of your eyes, but basically those are understood as an eye or as a mouth or as a hand, right? So that's the basic idea behind this, like to understand that this chunk of the image is pretty similar to this one. And because you want to basically feature or match the pieces of this image, right? For example, like this, you have one piece, another piece, and another piece that are, let's say, like the relevant chunks of your image. Then you want to compare or train a machine to understand that. And you will see that that same pattern, for example, can repeat in the image. And what is the first principle of convolutional neural networks is this idea of filtering. Basically, you will create a bunch of image filters to perform a calculation over the full image, right? And those filters basically will be something that you will feed into the network. We will see with parameters, like when we code this, that you will determine how many filters do you want to use in your image to make the calculation. So in this case, for example, this is what a filter looks like, right? It's just a chunk, a piece of the image that you will basically use to do some calculations. So what happens is that you have like different steps, right? And the first step is line up the feature and the image patch. I will explain what that is. Because basically this idea of filtering is like doing like some sort of matching. Then multiply each image pixel by the corresponding feature pixel, add them up, and then divide the total number of pixels in the feature. So what will happen is it's a process of downsampling like this. You will process your image through this filter, so you will get like a smaller and smaller image each time until you will basically get a specific value. So basically what will happen is that you will get the patch, basically the first filter, and you will multiply with a chunk of the image with the same grid size, basically, and you will multiply this, and then you will basically add the results. So if we perform this operation in the image, you will see that something like this will happen. We'll start multiplying, right? And you will get a new set of values, right? I'm multiplying like the first upper corner of the filter with the first upper corner of this part of the image, and I'm getting new results. So you will get a new pattern like this, just by performing that calculation. And that basically operation will go through this idea that all the new values that you get, you will add them up, and then you will divide it by the total number of pixels to get, let's say, like the average. Right? So what you will see is that this portion of the image will turn into one number. So basically, you will see that this is a process of downscaling something. If you repeat the process with another part of the image, you will see that you go through the calculation again, and then you will add the results. So that part of the image becomes just one pixel value that in this case is 0.55, right? So we can do like the calculation, right? We can do that, this calculation here. We won't do it. I will give you the answer, right? So basically, you will see that some pixels like contributes, right, +1 or subtract +1 to get like a specific value. So what happens here, right, is that through this idea of these filters that you specify at the beginning will be put against this original image to get a set of values. So something that was like 1, 2, 3, 4, 5, 6, 7, 8, 9 becomes a 1, 2, 3, 4, 5, 6, 7. So basically, you downsample your image, right, from 9 pixels width to 7 pixels width. And you will be wondering, like, why? I mean, why 7? And that has to do with other parameters that I will explain next. That basically will give you this downsample or this idea of like filtered image, right? So when you try like every possible match, you will get this, right, a set of values. And again, you will get, let's say you're working with 3 filters. So basically it's like you select 3 parts of your image and you calculate this against your image, like in this case, like 3 times. You will get 3 versions of this image. That is what's going on, right? So you will get a first set of values, a second set of values, and a third set of values or grids. And then, or basically, that is a convolutional or convolution layer. That basically is a set of new images from this operation. But we still don't understand how that calculation happened. It's like why something that has like 9 by 9 pixels became something that's 7 by 7. And basically it's because of that idea of downsampling. And that has to do with parameters such as the window size, basically like what is the size of that submatrix that you're using to produce those filters. Then you will pick a stride that basically has to do with how will you go over the image. Basically, you will use this patch to sweep across like all the pixels in your image, and basically you are specifying the step. So I will explain it graphically next, and then you will walk. Basically, you will do a walk of your window across your filter images, and then from each window, you will take the maximum value, right? So what will happen is exactly this, right? You will basically produce this initial filter images, this convolution layer, and then you will do something that is like the pooling, right? First, you will do a calculation that will go from 7, in this case, pixels to 4, right? Because you will perform a similar calculation as before, and you will, sorry, you will pick always the maximum value of this window here. And then you will walk according to the stride value. So basically the stride, in our case, the window size is 2 by 2, and the stride is also 2, meaning that you will move your window 2 pixels to the right. And from here, you will do this pooling operation and you will get the maximum value. And then you will continue like doing this. So you will pick 0.55. When you get here, basically you see that you run out of pixels, but you still will pick the maximum value. And then because your stride is also 2, then when you cannot move more to the right, you move to the left. Basically you walk through your image to get a new set of values, right? So your filter images, according to the filters that you use at the beginning, become this downsample layer, right? So basically a stack of images becomes a stack of smaller images. And what you want to do at steps when you do the downsampling, you want to add like some non-linearity by applying these famous activation functions to the filter outputs. For example, we will use ReLU as rectify linear units. So you will get this value of 0.77, and you will apply this this idea of excuse me, this activation function. And what this rectify linear unit is doing is just removing negative values, right? This is what this activation function is doing. You will find that sometimes you will use like sigmoid function that basically is like smooths the transition between values, basically. As they get close to 0, they smooth the values, or close to 1, they smooth that value. In this case, the rectify linear units, they just get rid of negative values. So this is why you see when you find a value that is negative, it just turns to 0. And you will get something like this as a result. So basically, a stack of images becomes a stack of images with no negative values. That is another principle of the convolutional neural networks, because of that ReLU activation. And the layers get stacked. So the output of one becomes the input of the next. So let's say you have a 9 by 9 input image or grid of pixels, and then the output is 7 by 7. That 7 by 7 grid will become the input of the next layer that can, for example, become a 4 by 4, and so on and so forth. So when you have this, you go through a convolution, then you apply the activation function, then you do your pooling, basically to pick the biggest values, and you get the smaller images. And the idea behind convolutional layers is that they get better if you stack more of those layers, right? So as you can see here, that sequence between a convolution, applying filters, removing negative values, and then selecting the highest values of those grids gets repeated, right? In this case, you start with the convolution, ReLU, you do the pooling, basically you downsample, then you do convolution, ReLU, then you do pooling until you get something like this, right? Smaller and smaller versions of your image. And what you do in the end, basically you need to express this in the form of a fully connected layer. Basically, you need to go from something that is a grid type of data to a linear type of data. So basically you want to reduce the number of output data in the form of your labels. So let's say you're trying to classify handwritten digits, and you know that you have 10 labels from 0 to 9. Basically, your fully connected layer will transform a grid of pixels into just like a linear array, basically like a linear set of values. In this case, like with size 10. And then you will pick the highest number. So in this case, what we will do, we will basically like flatten. This is pretty similar to what happens in Grasshopper if you have used Grasshopper. Basically a list, you flatten that list and you get like just one big group of digits. So with that, basically you can perform the calculation if something is classified as an X or a 0. And those fully connected layers can also be stacked. So that is like the main characteristic of this new architecture, is that you can stack, when you put everything together, a set of pixels produce a set of inputs to the final outputs. So in this case, for example, we have like 2 fully connected layers, and what you will get in the end, when you start, for example, with this image that it was 9 by 9 pixels, you will get always 2 values, because we have 2 classes that we want to classify, if something is an X or is an O. And those values basically will give you, like in this example, like this toy neural network, if something is a 0.92, I mean, a value of 0.92 and 0.51. So you see that, yeah, the highest value corresponds to an X. So your network is basically working because it's classifying this as an X. So basically, like, where do all the magic numbers come from, right? So like the features in convolutional layers, and the weight. That is a question that it was asked before in the presentation. And there is, and the answer basically is something that is called gradient descent, and one operation that is called backpropagation. We won't go into like full math explanation. I'd rather do like this explanation through like more graphical thing, because it's like closer to us as designers, architects, and so on and so forth. And I think for learning purposes, this is more useful to explain everything in a more graphical way than just like numbers and like formulas. Believe me, like after many years of architecture and making models, the sniffing glue basically fried my mathematical processor. So I don't want to go into like deep math. I suffer and I cry tears in machine learning classes here at MIT at course 6, that is the computer science. So I'm beyond that. I finished my classes, so I don't want to do that anymore. So basically what happens, the backpropagation is this idea of error, is having the right answer, the answer that you want to get, minus the actual answer that you're getting from your network, right? Those values, 0.92 and 0.51, will be useful to calculate the error of the current state of your network. So in this case, we know that the right answer for our network should be 1 if this is an X, right? But we got the actual answer as 0.92. So our error is 0.08, right? And for the 0, the right answer was 0, right? We wanted to say like, if it's an X, it's a 1, if it's an O, it's a 0. And our actual answer was 0.51. And the error, in this case, is 0.49. That gives us a total, like adding like those 2 values, of an error of 0.57. And we use gradient descent. So for each filter parameter and weight, we adjust it a little bit to decrease the error. So to do this efficiently, we need to calculate the derivative of the error with respect to the parameters. So basically that's what you're doing. You're using gradient descent. That is like one of the most used like techniques. You have a stochastic gradient descent, and you have like many, let's say like ways to calculate your error. In this case with gradient descent, basically you calculate the derivative of the error with respect to the parameters. And you can compute the derivatives using the famous chain rule that I won't explain here, but if you go to like, because it's long and it will take time. But if you go to, I don't know, like Khan Academy, what is the chain rule? If you don't remember it, I already forgot what it is. I mean, I can do it if I spend a day remembering it. But basically, that's the way it happens. So what is important to know here, beyond like the right input parameter format or shape, right, that I told you, is also like something that are called the hyperparameters. You will see this a lot when you go to like a GitHub repository that you download to use a model. Especially, it's not that important if you want to use a model, but if you want to train something, usually like machine learning architectures and models are highly sensitive to this hyperparameter. So for example, here, imagine this as knobs. You have like certain knobs that you want to move, right? Just like grasshopper sliders, for example. And in this case, for convolutional neural networks, you have the convolution, basically the number of features that you want to use, the size of those features, the pooling for the window size and the window stride that I explained before, and also the number of fully connected layers, the number of neurons as output, right? So the architecture is like also like, how many of each type of layer do I want to use and in what order, right? And it's important also to acknowledge that this is not useful only for images, right? Basically, this is useful. This is a technique that has been useful for us to apply to 3D data. So basically, what I'm trying to say here is that the closer, basically like any type of data that you can express in the form of an array can be fed into a convolutional neural network. So for example, sound, right? Sound is something that you can express as a matrix. And if you have that, you can input this to a neural network to train it and so on and so forth. So yeah, that's the idea, right? So for example, if you have images, columns of pixels, rows of pixels, or sounds, for example, you can have something that is expressing time steps versus intensity in each frequency band, right? And you can express this and you can train something. Text, for example, position in a sentence versus words in the dictionary. There are some limitations, of course. Convolutional neural nets only capture local spatial data. If the data can be made to look like an image, convolutional neural networks are less useful. That's the idea that I try to express. But if you're interested in using this, if you can express something as a matrix, convolutional neural networks is basically what you want to use. So for example, like customer data, name, age, address, email, purchases, browsing activity versus like customers. You can have that. Or and there is a rule of thumb that if your data is just as useful after swapping any of your columns with each other, then you can't use neural networks. That has to do with like, yeah, the way as this works. So in a nutshell, convolutional neural networks, or CNNs, are great at finding patterns and using them to classify images. So this is one demo that I will, let me see if I can open it. So I can show you graphically actually what is going on. Oops, and this is a principle that is also used in, for example, like style transfer. So basically, because you're learning the distribution of an image, basically you're learning patterns in an image. You can, this principle was used also to do this famous style transfer, that you can basically map the distribution of one picture, for example, to the painting that you have here. This is how Alderson is a professor of computer science, and he's applying to his image this painting, right? And you get an image like this. should I want to continue with this? Let me see. No, we won't go through a style transfer now. I just want to show you this before we take a small break, and then we will start. I will send this link here, and I have a question. Yes, I know that it's. Yeah, I will send. I'm recording this Zoom meeting, so if you have to leave, that's fine. Sorry for the time changes. Anyway, so I put the link. So if you go to this link, you will see that this is the graphical demonstration of what I just explained. So for example, I will write something that is like a 1. You can draw here, and you see what is going on. So basically, you have a set of parameters that are working with this idea of producing filters. So in this case, we're filtering this image with 5 filters. So this is why we're getting from one image a convolution layer of 5 filtered images. And then we do the pooling. Basically, this is operation of max pooling, getting the maximum value of the pixels. So we get a stack of like low resolution images, and then by performing the same operation, the convolution, and then the downsampling, and then what is interesting here is that when we get to like a point where we don't have more downsampling operations in our architecture, we pass this through a fully connected layer, meaning that basically you're connecting all the pixels, right? And then you are reducing this to another, basically you're reducing the dimensions of this list by performing max pooling or other operations, right? And then basically you use this fully connected layers, basically saying that I don't know how many pixels do we have here. So let's say you have 700 pixels, and then you say like, okay, I will apply another fully connected layer to reduce those 700 values to, let's say, like 300, and then to reduce those values from 300 to only 10. So in this case, what you see here is that according to the color, the more cyan the color is, it has the biggest prediction. So if I click here, you can see that the output is 0.11. That is the maximum value, and it's correctly classifying this as a 1. So what you see here, for example, like the second guess, the second highest value was this, a minus 0.66. That it guessed like in the first place that, oh, this is a 1, but it could be a 9 as well. So let's see if I want to draw something that is like a 0, but kind of looks like a 6. And actually, yeah, it believed that the second guess was an 8, but it performed really great with the 0. So that's the idea. I mean, you can play a little bit with this. We will do one thing now. We will take a 10-minute break, and then during the break, take a bio break, drink water, or coffee, or whatever. But I want you to go to Colab, Google Colab. I will put it here, colab.research.google.com. So we will use this as our platform for coding. Oh, and I didn't send you the link before, so because I sent it to.
Can we have the link to that other site too to see it? It seemed really interesting.
Sorry, it's just that someone wrote me a message and I sent it only to her. That is the other website. But go to collab.research.google.com. If you have a Google account, log in with that. And what this will do, basically, it will start this platform that is really good for coding. And it's based on Python notebooks that I will explain. So let's take 10 minutes. In my case, it's 12:10. So in 10 minutes, we will start again, okay?